These 6 trig functions can be defined off of a right triangle instead of using a unit circle. So here I have a right triangle with this one right angle, and I've labeled this angle theta. I want to put a few other things on here. For starters, the side that is opposite the angle is called the opposite side, so I'll just put opposite abbreviated like this. This side here is adjacent to this angle, so I'll put ADJ for adjacent. And finally, this side, well, it's also adjacent to this angle. This is referred to as the hypotenuse. It's the one that is opposite the right angle. So I'll abbreviate that like this for hypotenuse. So using these 3 sides of any right triangle, you can define these 6 trig functions. Sine is defined to be the opposite side, the length of it, divided by the hypotenuse. Cosine is the adjacent side over the hypotenuse. Tangent is the ratio of these two things, which is the opposite over the adjacent. And when it comes to cosecant, secant, and cotangent, these are the reciprocals of these 3 trig functions. So basically, we're just going to flip all of these fractions and put them here. So that means cosecant is the hypotenuse over the opposite side, and secant will be the hypotenuse over the adjacent side, and cotangent will be the adjacent divided by the opposite side. If we focus on these 3, the 3 main ones, people sometimes remember this by writing down so, ka, toa. And so this stands for sine is the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse, and tangent is the opposite over the adjacent. So if you can remember that, you can recall these definitions, and these come from flipping those fractions. An important theorem when dealing with right triangles is the Pythagorean Theorem. So if I label sides of this right triangle off to the side as A, B, and C, A squared plus B squared is equal to C squared. And that's what the Pythagorean theorem states, that if you square this side and you add it to the square of this side, it'll be equal to the square of this side. And that only holds in a right triangle. So for example 1, applying this theorem, so if you have a right triangle, and this side is length 4, and this side is length 3, can we figure out the length of the hypotenuse, C? I'll use this theorem to figure it out. So I guess what I'll do is call this side A, this side B, and plug this information into the theorem. So if A squared plus B squared is equal to C squared, we have that 4 squared plus 3 squared is also equal to C squared. 4 squared is 16, 3 squared is 9. And if we add these two together, we get 25 is equal to C squared. Now you could think about a number that makes this true. For example, I know if you square 5, that's going to give you 25. But another valid approach is to take the square root of both sides. Now, technically, when you do this, the square root of 25 is 5. But if you use this process to solve for C, you get a plus and a minus. However, since we're talking about lengths, only the positive solution makes sense. So this determines the length of side C, which it must be equal to 5. So in this example, on this right triangle, I'd like to evaluate the 6 trigonometric functions for the angle here, theta. So if you'd like to start this, maybe a good place to start would be by using sine. Sine is defined as the opposite side to the angle over the hypotenuse. And so this fraction is going to be equal to, well, this is the opposite side, but technically here, we don't know the hypotenuse. In the previous slide, we did figure it out, and we saw that it was equal to 5. So when trying to evaluate trig functions based off of an angle in a right triangle, you may need to solve for one of the remaining sides. We already happen to know this one, And so the opposite over the hypotenuse is 3/5. Continuing, cosine is the adjacent over the hypotenuse. And in this case, the adjacent side to the angle is 4, the hypotenuse is 5, and so we have 4/5. If we want tangent, tangent is defined as the ratio of these two things, but off of the triangle, you can say that is the opposite side over the adjacent side, which would be 3/4. It's the opposite over the adjacent, and that would be 3/4. For the other three trig functions, cosecant of theta is the reciprocal of sine. So that is the hypotenuse over the opposite, but I really can get my answer just by looking here. I know if I flip this fraction, I would get 5/3, and that's the answer for cosecant of theta. Same idea for secant of theta. It is the reciprocal of cosine. So if I look here, I can flip this fraction, so I get 5/4. And lastly, I want cotangent. What is cotangent of theta? That's going to be the reciprocal of tangent, which is flipping this fraction, and I get 4/3. So these are the 6 trig functions based off of this angle. There wasn't much to simplify. This really came from knowing that this side was length 5, and then how these things were defined off of the triangle itself. Off to the side here, I have a right triangle, and I've already labeled all of the sides and the angles off of it. So this is a 30-degree angle. This is a 60-degree angle. This side is length 1. This side is length the square root of 3, and this side is length 2. Based off of that, can we figure out what cosecant of 30 is? And, well, what is secant of 60? So let's actually figure out those values. If you want cosecant of 30 degrees, okay, cosecant was the reciprocal of sine, so that's going to be the hypotenuse over the opposite side. So that is 2/1. And this simplifies like really easily. It's just, 2. So that's cosecant of 30. Okay, what about secant of 60 degrees? Now this time, secant, just to maybe put this up here, this is the reciprocal of cosine. So this is the hypotenuse over the adjacent side. But you have to know which angle you're referring to. So here we're talking about the angle of 60. Now that doesn't change what the hypotenuse is. The hypotenuse is still 2. But this time, the adjacent side is going to be 1. And the reason for this is, if we're using this as our angle in the function, it is this side that is adjacent to the angle, while this one is still the hypotenuse. All right, so in terms of figuring out what the value of this thing is, the hypotenuse is 2, the adjacent side is 1, and so actually the answer is also 2. It turns out that cosecant of 30 and secant of 60, they're actually the same thing, but that makes sense if you switch these two angles. You're always talking about this side and this side. Now, I didn't ask for this in this problem, but I say we figure it out. What is cosecant of 60 degrees? And what is secant of 30 degrees? What if we flip this around a little bit? If we want to know cosecant of 60 degrees, we're talking about this angle over here, and cosecant is going to be the hypotenuse over the opposite. So actually, this time, cosecant of 60 is going to be 2 over the square root of 3. The hypotenuse never changes, but here, the opposite side is going to be the root 3. Technically, this answer would not be accepted if you entered it into MyLab, and that's because it has a root in the denominator, an irrational number. There is a nice trick that you can do to rationalize the denominator, and that is by multiplying the top and bottom by this denominator here, the square root of 3. The reason that this rationalizes the denominator, because if you multiply the square root of 3 times the square root of 3, it's equal to 3. Now, in the numerator, you have 2 times the square root of 3, But written this way, this number and this number are equal, but there is no irrational number in the denominator. Now to figure out secant of 30, so I want to know secant of this angle. This is the reciprocal of cosine, so that's going to be the hypotenuse over the adjacent side. So this time, this is the adjacent side to the angle. So again, we get 2 over the square root of 3. And we already did the work for this. I know if we rationalize the denominator, this is equal to 2 root 3 over 3. And again, we're getting these two values, and they're equal. So these were both the same. This really is no surprise when you're using functions like cosecant and secant and sine and cosine, for example. 30 and 60 degrees, the other two angles of a right triangle, they add up to 90 degrees. These are called complementary angles. And it turns out if you look at cosecant and secant of these two angles, you get the same value. The same thing is true for if we looked at sine and cosine, as well as tangent and cotangent.